Good morning to all of you. I think that all of you have enjoyed very much the first lecture by Professor Suman Chakraborty, which told about the motivation of learning fluid mechanics and how does the science of fluid mechanics play the role in all spheres of our life. Now we will start formally the course fluid mechanics. To start with, we will first learn what is the definition of fluid. As we know that the matters are usually exist in three states: solid, liquids and gases, and these liquids and gases we call as fluid. From our kinetic theory of matter, the knowledge of kinetic theory of matter, we know the differences in these three states are due to the spacing of molecules within these substances, that is their distance of separation, and the intermolecular force of attraction known as molecular cohesions. But in the study of fluid mechanics, we will go through the definition of fluid as distinct from that of a solid from the mechanics point of view. Now, from the mechanics point of view, a solid is a substance which, when acted upon by an external force, resists the force under static equilibrium after going through a finite change in its dimensions and shape, which is called as deformation. That means a solid undergoes a finite deformation, changes in its dimension and shape, and then resists an external force under state of static equilibrium. Moreover, it has a preferred shape to which it relaxes when the force is withdrawn. Whereas a fluid cannot do so. It can neither resist external force under the state of static equilibrium after a finite deformation, nor has it a preferred shape to which it relaxes when the force is withdrawn. These are the basic differences between a solid and a fluid from the viewpoint of mechanics. Let us understand this through a simple diagram. Let us consider a solid A, B, C, D, a solid. When an external force is applied to it, let us consider a tangential force applied to the solid. Then it has a finite deformation and resists this, it is A, B, C dash D dash. It goes to a position A, B, C dash D dash, where it has a finite deformation and resists the force under static equilibrium. And when this force F is withdrawn, then if the solid is a perfectly elastic solid or within the elastic limit, the solid relaxes to its preferred shape, the original shape A, B, C, D. But what happens in case of a fluid? If you consider a fluid element, then we have to consider like that. Let us consider between two parallel plates a fluid is contained between two parallel plates. Let us consider a fluid element like this, like a solid element, as we considered A, B, C, D, fluid element. Okay? Now, if we want to apply a shear force like this on this fluid element, this can be made by making one of the plates moving in the direction, which may, because of the drag between the solid and the fluid element, can create a force like this as a shear force on this fluid element. And if it is done, it will be observed that this element goes on changing continuously in its dimension and shape like this. Like this, it goes on changing its shape. Let B dash, A dash, B dash, C dash, D dash, again continuous change in the shape, continuous change in the shape, A dash, B dash, C dash, D double dash. That means from A, B, C, D, A, B dash, C dash, D dash, A, B dash, C dash, C double dash, D double dash, that means this goes on continuously changing in its shape, and this continuous change in shape constitutes the flow. The flow is constituted by this continuous change in the deformation or the shape when this force is applied. Moreover, if the force is withdrawn, that the plate is stopped, force is withdrawn, the fluid element will not come back to its original shape, it will remain on it to its deformed shape. That means it cannot relax to a preferred shape which the solid does. So, these two ways the fluid and the solid differs. Now, here one another important thing is that this force, even if it is very small, however small it may be, even infinite small, the continuous deformation will take place. The implication of this is that there are certain classes of substances, or you can take that there are certain classes of solids which after a threshold value of this F goes on continuous deformation and they behave like a fluid. This is known as, first of all let me write solid, and this is fluid, and this is known as plastic, which continuously flow after a threshold value of the force, when the force, this external shear force exceeds certain limit. So, they behave partly as solid and partly as fluid. So, the distinction between solid and fluid is very hazy in that case. This is the fluid, and the examples of such substances are paints, this plastic paints, then we can have paste, jelly, these are some pitch, some polymer solutions, these are examples of such fluids, polymer solution. So, therefore, we see that a solid resists the external stress under the shear stress. For example, here we have shown under static equilibrium condition and relaxes to the preferred shape when this is withdrawn, whereas the fluid goes on continuous deformation under the action of shear stress, however small it may be, and cannot relax back or cannot come back or relax to a preferred shape. So, these are the two main differences. So, because of that, a perfectly elastic solid is known as perfect memory substance, whereas a fluid is known as zero memory substance, because it cannot come back to its original shape, zero memory substance. So, there are in this context I tell you that there are certain substances which possesses both the property of the elastic solid and the property of the viscous fluid, and known as viscoelastic substances. These are solids or fluid which possesses both elastic and viscous properties, and they are known as partial memory substances, which under when the force is withdrawn they come back partial, this is not coming, partial viscoelastic substances. These are in between substances which possesses both viscous property and elastic property, and they are told as partial memory substances. Partial memory, MEMORY, slightly bigger, no? Partial memory substances. Partial memory substances. It is not. Okay. Viscoelastic substances. Okay. So, therefore, with this definition, with these changes, we define the constitutive equation. Now, let us tell Professor Suman Chakraborty in the next lecture will tell you what is constitutive equation. Usually, the constitutive equation, now before going to tell you the constitutive equation, I tell you that we have described this the difference under the action of a shear stress. Now, let me tell about the normal stresses, that solid and liquid, they behave almost identically under the normal compressive stress or normal compressive force. Stress is force per unit area, which will be discussed afterwards. So, under normal compressive stress, whereas liquid, a solid can support the tensile stress, but the fluids cannot support the tensile stress. But some fluids support the tensile stress. This is not very usual depending upon the degree of their molecular cohesion. Usually fluids do not support the tensile stress, whereas the solid can. Now, I come to constitutive equation. Now, the constitutive equation will be told in details afterward. Now, a constitutive equation of any material relates this force with the change in its dimensions, linear dimensions and angular dimensions, which we call relates with its deformation. Now, in case of solids, now forces are expressed in terms of stress, that means the force per unit area, and this relates stress as a function of deformation. In case of solid, since the solid resists the external force or stress under static equilibrium, after a finite deformation, the constitutive equation for solid are expressed, solids are expressed in the form of stress as a function of deformation, whereas for fluids, this is expressed stress as a function of rate of deformation, since there is a continuous deformation taking place. There is a continuous deformation taking place. That is the reason for which the constitutive equation is defined as stress as a rate of deformation, whereas for solids stress as a deformation, since the solid resists the stress with finite deformation under static equilibrium. So, these are in short the differences between solid and the fluid from the viewpoint of mechanics. Okay. Next, before studying fluid mechanics, we must know one thing, what is known as continuum. It's coming? Coming? Continuum. It's coming or is becoming slow, huh? It's coming. Sorry, please wait whether it is coming. And this is the problem actually, the teaching will. No, pressing and slow. Oh, it requires tremendous pressure. The দুটো না একটা হ্যাঁ কন্টিনিউয়াম কন্টিনিউয়াম ইউএম continuum. You understand? Continuum. Now, we will discuss before going further what is meant by continuum. Now, as we know that all substances are composed of number of molecules. This we know from kinetic theory of matter, number of molecules which are having ceaseless motions in ceaseless random motions with the magnitude and directions varying randomly. Therefore, the properties of any matter has to be expressed in terms of the behavior of all the molecules, because properties of any matter or any substance should definitely arise out of the properties of the molecules or the behavior of the molecules constituting the substances. So, therefore, whether it is solid or fluid, it is always recommended that its properties are to be calculated from the properties of the molecules or behavior of the molecules which compose that substances. But it is found that this task becomes formidable in certain cases. Let us take an example. In case of gas, let us consider gas. As we know that solid, liquid and gas, the spacing between the molecules are relatively much less in case of gas. The spacing between the molecules are usually described in terms of mean free path, that is the statistically average distance between the collisions, successive collisions between two molecules, and this mean free path is relatively much larger in case of gas as compared to liquid, and in case of liquid it is still larger as compared to solid. So, let us take an example of a gas where the molecular spacing is relatively larger or the mean free path is relatively larger. Now, we know in case of an ideal gas, the molar volume of an ideal gas contains 6.02 into 10 to the power 23, huge number of molecules for an ideal gas, if you know, per molar volume. This is known as Avogadro's hypothesis, this number of molecules. So, therefore, for a molar volume this number of molecules are there. If we want to study the dynamics of the molecules, then what we have to do? For example, we take that three translational velocities. Let me write three translational velocities or translational motion in three coordinate axes, three translational velocities and three rotational velocities, rotational degrees of freedom. If we take only these three rotational velocities in a coordinate frame of reference, then we have to have 6 into, for each and every molecule we have these three velocities, translational, three rotational velocities, 6.02 into 10 to the power 23, it is coming, no? Number of equations we have to solve. Now, you see that for a molar volume, if this be the number of molecules, then if we have to find out or study the translational and rotational velocities in a frame of coordinate frame of reference with three directions, we have to solve 6 into 6, 36 into 10 to the power 23 number of molecules, number of equations, even in a molar volume for an ideal gas. So, therefore, you imagine how much it is formidable to go with this approach of molecular behavior, that molecule to molecule, each discrete molecular behavior. So, therefore, this approach is very tedious and sometimes it is formidable. So, therefore, as a clue, as a what coming away out of these difficulties, the two approaches have been originated. One is known as microscopic approach, microscopic or statistical approach, statistical approach. Two approaches are there. The microscopic and statistical approach, what they do actually, instead of going for each and every discrete molecular behavior, we consider the statistical average behavior of the molecules at a location, and this is taken as the property which is being manifested by the behavior of the molecules. That means the statistically average behavior of a group of molecules being manifested in terms of the property of that particular location, and this is found out from the studies at the molecular level, and this is known as microscopic and statistical approach. Another one is the macroscopic approach, macroscopic approach, macroscopic approach. This is my problem actually. If you be little fast, macroscopic, sorry, what happened? This is coming. No, sorry. Macroscopic approach. In macroscopic approach, it goes one step further. What does it do? It senses the property by an instrument which captures the gross average behavior of the molecule at that location, which is being manifested as the macroscopic property at that particular location, and this is being censored and captured by that instrument. This is known as macroscopic approach. Try to understand again that one is the microscopic approach where the statistical average behavior of a group of molecules at a location is calculated and is manifested as the macroscopic property at that location. And another approach is that where a sensor captures in a similar way the gross behavior of the average gross behavior of the molecules, which is being manifested at the particular macroscopic property. Just an example I am telling, when we talk about the pressure exerted by a gas on certain location of a solid boundary, it is actually causing by the change of momentum of all molecules which are being bombarded or which are colliding with the surfaces. So, what happens in the statistical approach is that they calculate a statistical average of the change in momentum as the measure of the forces exerted on the wall from which the wall pressure is calculated. That is the microscopic or statistical approach. Another one is that this is a macroscopic approach which goes one step further. They are a measuring instrument senses the pressure at a location, which is again the gross average behavior of the molecules. That here molecule behavior means here is the change of momentum, gross average values of the momentum change of the molecules colliding this surface as manifested by the pressure and sensed or measured by that instrument at that particular location. This is known as macroscopic approach. Now, if we take the results from this macroscopic approach and use that property and try to resolve that property both space wise, that spatial resolution, and the temporal with time wise, by applying the differential equations or by measuring through the same instrument at different locations at a different time, then we can describe the continuous variation of the property throughout that medium. And where we can do so is known as, the medium is known as continuum. Continuum. It is what happens that this is a real problem. If this has to be conti, C is coming, no, is known as, no, this way it will be tough, I am telling you. If these things cannot be written and cannot be shown, so how I will, so one known as, so I have to talk only in that case. What is this? Continuum. All right. This is known as continuum. Let me talk, it will be difficult. You see that here the way it has to be written, I do not know. So, let me tell you, understand that this medium where this is possible is known as continuum. Now, the question comes, very important question, how is it accurate? That means at a particular location, if a measuring instrument senses the gross average behavior of the molecules, then how I am sure that this gross average behavior of the molecule is correct enough? What is the level of uncertainty in the measurement, so that we can correctly describe the property before we want to make a resolution by the application of differential equations, or by again measuring the property at different locations by the instrument. Now, the question of accuracy comes, but where it can be done, let us first assume that okay, it is accurate. Then if we can do it, then in a medium where you can do it with accuracy, that medium is known as continuum or continuous medium, where we can describe a continuous variation of the property as manifested by the gross average behavior of the molecules at a certain location. Now, the question comes, what is the accuracy of that? The accuracy, the question comes because of the fact, when we call a location, we always call a infinite small volume at a particular location. If we consider a point, a location, if it is specified by a point, theoretically a point has 0 volume. Now, you see, whatever may be the number of molecules in a substances, but molecular distance, then average distance between two successive collisions is mean free path, which is specified as the molecular distance of separation, which is not 0. So, therefore, it may so happen at any instant of time, at any point which has got 0 dimension, may not have any molecule at all. So, therefore, the question of accuracy comes, which way we define a particular point or location under concern, that how small the volume will be and how much molecule will be there. Let us understand that through an example like this. Let us consider a fluid medium. Let us consider a fluid medium, okay, a fluid medium. Let us consider a fluid medium. Let us consider a fluid medium. Now, a location is specified, let us consider by a very small volume dV. Now, what happens if we want to calculate the density at that particular location surrounded by that small elemental volume dV? Now, what happened at any instant of time, the density is the calculated by the density of the number of molecules residing in that particular locations. Now, if the number of molecules in that location is very small, then the uncertainty in finding out the density will be very high, or you know that molecules are coming randomly into the volume and going out of the volume. And if the number of molecules residing in the volume is of the order of magnitude of the number of molecules coming into the volume and going out of the volume, then also uncertainty in measuring the density will be very high. So, therefore, it is a common sense that tells what will the remedy. One remedy is that the volume should be larger, so that we are sure, we ensure that more number of molecules will be there, huge number of molecules will be there at any instant of time, as compared to the number of molecules coming in or going out. So, therefore, the level of uncertainty will be reduced. On the other hand, if we expect that the number of molecules will be, what happened? If the number of molecules are closely packed even within the small volume, then also the uncertainty will be less. So, therefore, the accuracy will depend upon how many molecules are residing within the volume, it is the molecular density. Now, you see that the choice of this dV volume is restricted by our spatial resolution, which is dictated by the size of the geometry or size of the system or the geometry of the system, because we cannot make this very high, so that the resolution, spatial resolution is hampered. So, therefore, there is a restriction on this size dV, and the number of molecules which are residing within the small volume depend upon the molecular spacing, that depends upon the state of the fluid. For example, for a gas, if the pressure is low, for example, for a gas, if the pressure is low, then what happens? The molecular distance is more. So, therefore, it depends upon the molecular spacing and also depends upon the dimension of the volume to be taken, which is indirectly related to the spatial resolution which you want, that is being controlled by the geometry of the system. So, therefore, two important things are there. One is the lambda is the mean free path, another is the characteristic dimensions of the geometry. This characteristic dimension LC, that determines the small volume to be taken, and lambda determines the mean free path. Now, if lambda is very less, then what happen? So, accuracy will be very high even if for a small volume is there, or at the same time if LC is very large, we can have a relatively bigger volume, so that the uncertainty is reduced, more number of molecules are there to show the accurate behavior through their gross average behavior. Therefore, a ratio of the mean free path lambda divided by the characteristic dimension LC is defined as the Knudsen number, is taken as the criteria, criterion of continuum or continuous medium, as I told. So, therefore, it is clear continuum. So, this ratio, so therefore, again we understand that lower is the value of lambda, higher is the value of Knudsen number. Higher is the value of lambda, lower is the value of lambda, lower is the value of Knudsen number. Higher is the value of LC, lower is the value of Knudsen number. So, when Knudsen number is low, means that the molecular mean free path is low, then our accuracy is more, or LC is large, the characteristic dimension of the system is large, so that we can afford to have a relatively larger volume to represent a location. So, there also the number of molecules, probability of number of molecules residing will be higher. So, uncertainty in the measurement of the property as the manifestation of the gross average behavior of the molecules will be reduced. So, therefore, we see this ratio as uniquely determines that. That means, a lower Knudsen number, that means the lower mean path or a higher characteristic length of the system is favorable for accuracy of the measurement of the macroscopic property as a gross behavior of the molecular behavior will be there. That means, the continuum approach will be much more valid, while the reverse is also true. That means, if the Knudsen number is high, that means the mean free path becomes high, which I just explained, depending upon the state of the system. For example, gas at rarefied pressure at very low pressure near vacuum, this lambda becomes very high, or the length becomes very low on the other hand, which Professor Suman Chakraborty told today's the applications in the microfluidics. The flow through a very small devices where the characteristic length is such that we cannot afford to have a higher dV. dV should be infinite small, it is vanishing volume, volume should be limiting to 0, dV should limiting to 0, because otherwise we cannot make a spatial resolution of the property in that microsystem. So, in that case also this continuum theory will be not valid, because then the mean free path will not be able to justify for more number of molecules to be there within this volume defined to represent a point to reflect that property. So, now I show you with this concept in mind that what is the information regarding these scales that you see in the table, that when Knudsen number is less than 0.001, we consider the flow or the medium to be continuous medium or continuum with no slip condition. It is written there, no slip condition. That means not only continuum approach will be valid, but at the surface Professor Suman Chakraborty explained that boundary conditions are very interesting for fluid flow, that depends upon the interaction of the fluid with the boundary. No slip condition is a condition which will be discussed afterwards in details, that the flow velocity with respect to the solid surface at the solid surface is 0. That is known as no slip condition. Again I am telling the tangential velocity or velocity along the solid surface of a fluid with respect to the solid surface becomes 0, that is the no slip condition, and this is a consequence of the interplay between the solid and the fluid by the force of attractions or the adhesion forces between the solid molecules and the fluid molecules, where the no slip condition will be valid. And here we see beyond 10 Knudsen number, this regime is known as the free molecular regime. From a Knudsen number of 0.001 to 0.1, the continuum approach is valid, but not with the no slip condition, but with the slip at the boundary surface. That means the fluid velocity relative to the solid surface, the tangential velocity of fluid is not 0. And from 0.1 to 10, this is a transition region where the validity of the continuum slowly becomes weak, and continuum approach ceases to be valid when the Knudsen number 10 is reached, beyond which we must go for the analysis based on the molecular dynamics, okay, the analysis for discrete molecules. So, this is free molecular regime. This is the criterion of Knudsen number for all our ordinary fluid mechanics studies, except flow of gases at extremely rarefied pressure, where Knudsen number becomes high in this range 0.1 to 10 or even more than 10, or fluid mechanics through micro devices, as Professor Suman Chakraborty explained. Nowadays with the invention or with the development of the MEMS micro electromechanical systems, the continuum approach is valid for all other cases of fluid mechanics. Okay, thank you. This is